Today we have Foling Zou, who will tell us about unital operads, monoids, and monads.
Yeah, thanks. Hello, everyone. I'm Foling Zou, and I'm now at Chinese Academy of Science in Beijing. And today I'm going to talk about some drawing work with Peter May and Rachel Ruoqi Zhang that we did back in the years, and we are revising this paper recently. So I think it's a nice time to talk about this work. So the plan of the talk is the following. First, I'm going to give some quick definition of operads and monads, and then say why they're interesting. And then I'm going to talk about symmetric sequences, which we call sigma sequences, and the lambda sequence that we are going to define, which is the object of study in our paper. And then in the last part, I'm going to talk about how to use this language to define factorization homology as an application. Right, so operad was invented from the work of Boardman and Watt using props, and then invented by Peter May, and who gave it this name. So it's a combination of operation and monad. Namely, we define an operad in topological spaces to be a sequence of spaces. So a sequence of spaces Cn for each n with a symmetric group action on the space, on each space, and it has structure maps like this, which can be thought of as composition. So the K space can be thought of as k-nary operations, and if you have K input and then you have K operations, you can compose them to have a operation of this many inputs. And you also have a unit that is a map from a point into the first space C1. And it needs to satisfy some compatibility relations. The first one says that if we have 3 chunks of the Cs, and if we compose here and then compose this way via this direction, or if we compose here first and then compose like this, then these two maps should commute. And secondly, this unit should serve as like a unit, which means that these two diagrams should commute. And last but not least, this structure map needs to be equivariant with respect to certain permutations in some way. And an algebra over an operad is a space A with maps like this. So basically, we are able to realize this CK as k-nary operation on this space. And this theta needs to be associative and unital, just like you would expect. So some examples include, the first one is the commutativity operad, whose n space are always just a point, and the structure maps are the obvious ones, the only ones. And algebra over this operad is just commutative algebra. And the second one is the Barrow-Eccles operad, whose n space is given by this space E sigma m, and the structure maps are induced by sigma k cross sigma n1 cross sigma nk into sigma of the sum of n's, just by so first these sigmas can be combined into a big sigma, and then this sigma k acts on that by permuting these blocks. And this map will induce a map on E of this construction. The details of this is in Ruoqi May. And algebra over this operad are called E-infinity algebras. Also, there's a more topological example, little n disk operad, dm. Here n is fixed, and the K space of this is is an embedding space, is a subspace of the embedding space of k copies of unit disk in Rn into the disk, such that each of these is just f of v is in the form of av plus b. So this needs to be embedded without any rotations or stretching. I mean, you can do radius stretching, but you cannot do ellipse ones. And the composition, the structure map is by composing the embeddings. And algebra over this operad are called the EN algebra. And why is this notion useful? In topology, string monoids are very rare and they are less common than the homotopy coherent monoids. So for example, here, n-fold loop spaces are always examples algebra over Dn, and they can be thought of as monoid in some way, but this tells us, well, this is the reason why the nth homotopy group is a group for n greater or equal to 1. But the commutativity of this group is only happens abelian group. It only happens if n is greater or equal to 2, whereas on the space level, we do not have strict commutativity for all n. We only have homotopy coherent commutativity. So this little n this opera tells us exactly how commutative this concatenation of loops are behaving. And using this operad may, in geometry of iterative loop spaces, had a recognition principle for n-fold loop spaces. So we have seen that n-fold loop spaces are Dn algebras, or algebras over the little n this operad, and they are also group-like. And it turns out that the category of group-like Dn algebra is equivalent to the category of n-fold loop spaces. And if we let n goes to infinity, group-like E-infinity spaces have the same homotopy category as connective spectra. And also, Boltzmann and Walt, they have a work which says that if you have an operad, you can construct another operad, WP, such that homotopy P algebra can be just this is the same thing as algebra, strict algebra over the operad WP. So, for example, the commutative operad above, if we do this W construction, WP, we will get an E-infinity operad. So this way, homotopy commutative algebra are just the same thing as E-infinity algebra. And using the language of operad, we could also study model structure on this category. So Berger, Modric, and Mendel, Pelov, Schobach, Kroll, Harper, and other people, they have studied model structure on operads and similarly model structures on their algebras. Right, and so far I have only talked about operads in space, and it is quite straightforward to see that operads and algebras can be defined in any symmetric monoidal category, V tensor I. In the example above, we are taking the space of the symmetric monoidal category, topological spaces, cross product, and a point. And we are just replacing the cross by the tensor product everywhere and replace the point by the unit. And for example, the unit map now is going to be a map from I to C of 1. And context of this could be an algebraic context where now we take the symmetric monoidal category of chain complexes. And we would have several interesting examples. For example, Ginsburg, Karpernov, they studied the Lie operad, whose algebra just gives us Lie algebra. And Gessler studied the homology of the framed little two-disk operad, and this is an operad whose algebra gives us what's called BV algebra. And now let's look at what the role the zero space play. The zero space C0 plays a special role. Basically, let's see if A is a C algebra, then we will have a map from C0 to A. So taking K equals to 0 in the structure map, we get a map from C0 to A, and we will have CK cross this map is compatible with the theta in this way. Well, on my screen it's a little lagging. Okay, right. So this is a commutative diagram. That's part of the data we need, a part of the structure we need for A to be a C algebra. So from this diagram, we see that C0 is in particular, C0 is a C algebra, and this map C0 to A is a map of C algebra. So C0 is the initial C algebra. And is my screen moving? Okay. So we say that the operad C is reduced if C0 is just a point, and we say it's based if we have a map from a point to C0. And in a general symmetric monodal category V, we say that it is unital if C0 is just the unit, and we say it is unitary if there is a map from the unit to C0. Okay, so now let me define these two categories, sigma and lambda. So sigma is the category of finite sets and based bijections. So we are taking these objects to be n for n greater or equal to 0, where each n means 0, 1, 2, the set 0, 1, 2 to n with the base point being 0. And lambda is the category of finite based sets and based injections. So its objects are in the form of n, and its morphisms are injections that sense 0 to 0. And by a sigma sequence, we mean a contrariant functor from sigma to V, which we will write as sigma op of V. And by a lambda sequence, we mean a contrariant functor from lambda to V. And when I write lambda op I of V, I mean this is a unital lambda sequence, meaning the zero space is the unit I. And by writing lambda op V and then a subscript I0, I mean it is unitary. So there is a map from I0 to this C, which is basically saying that we have a map from I to C of 0. So this is compatible with our notation above. So here are some examples. If we have a space M, and we can think about all the ordered configuration space on M, and this is naturally a symmetric sequence, but it is also naturally a lambda sequence. Because we not only can permute points, we can also forget points. In the second example, if we have a operad, then we definitely can forget, we will get a symmetric sequence. And if moreover we have a unital operad, then we can forget to a lambda sequence. So now if we have an injection from n-1 to n, that misses I, so I is from 1 to n, then we know how to send Cn contravariantly to Cn-1. Basically, Cn is isomorphic to Cn cross tensor I to the n, and then we map the I to C1, where it is hit in sigma I, and at the I slot so this is eta tensor dot 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 to, and at the I slot we use the isomorphism I with C0, and then at other slots we use eta. And the structure map here will send Cn tensor C1 tensor dot 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 tensor C0 tensor dot 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 tensor C1 to Cn-1, because now we have n-1 numbers of 1 and 1 number of 0. Oh, I was logged out. All right, so we have seen that if we have an operad, we can forget structures to get a symmetric sequence. And if we have a unital operad, we can forget most of the structure, but still remembers a little bit of it to get a lambda sequence. Now the question is, can we recover an operad from its underlying symmetric sequence or lambda sequence? So the answer is yes. And from now on, we assume that the symmetric monoidal category V is closed and also bicomplete. Then Kelly and also Smirnov observed in their papers that we can define some monoidal structure on symmetric sequence such that operads are exactly monoids in this monoidal category. And what we did in our paper is to generalize this to the unital case. So we can define some monoidal structure on lambda sequences so that monoids in that are exactly unital operads. I think so. Yeah, to the question of Doug. I wasn't so sure about their first name, but that looks correct to me. Okay, so here I'm working with lambda op V. Actually, it's a unitary lambda sequence, so I need to have a map from I to the 0th space. And then I'm going to have two kind of monoidal structure on this category. So the first one is Day convolution. It is symmetric monoidal. It's also closed symmetric monoidal. The second one is, we are going to call it Kelly product. And people have also, in the symmetric sequence case, called it composition product. So this name might be helpful if you already know what this is. This is monoidal, but not symmetric. But what is the day convolution? Let me just give a quick definition. Here, if I have two contravariant functors C and D, I can do the first line. I can do external tensor product of C and D, and then using the symmetric monoidal structure on lambda op, I can do left con extension, and that is going to be the day convolution of C and D. The unit for this day convolution is this I0. It is co-represented by the unit in lambda op, and this is purely formal. So in particular, if we examine what precisely is it, it is the unit at level 0, and it is the initial object at level greater than 0. And there is a concrete description of the nth level of this day convolution. So if I do the sigma version of it, meaning I do left con extension of sigma op cross sigma op to sigma op, then at the nth level, I will just get I plus j equals to n of di tensor ej. And then I do a symmetrialization of this. So that is the explicit formula for the day convolution in this case. And it turns out that if we do this for contravariant lambda sequence, then this is isomorphic to if we do it for viewing it as a symmetric sequence. So there's a map of the day convolution in symmetric sequence to the day convolution in lambda sequence. This map is an isomorphism. And this is not true for covariant lambda sequences. It's true for contravariant lambda sequence. And now let me give a detour to compare this with the theory of dendroidal sets. I've heard the word dendroidal set several times, and it's always mysterious to me. And I read a little bit about it. So a dendroidal set is a contravariant functor from the category of trees called omega to sets. And this theory was invented and studied by Hughes, Modrek, Weiss, and Sinsinski, and others. So the object of this category of trees include a lot of things, and let me just list some important ones. So there is this eta, which is just a single root. There is this C1 with two edges and a vertex, and there is this C2, C3, and so on. And we can also take a closure of these guys, C0, C1 bar, C2 bar, and C3 bar, meaning now we close them up by vertices on top. And the morphism between the trees should send edge to edge. It doesn't send vertex to vertex though. However, it should send a subtree with its outer edge to a subtree with its outer edge. So by outer edge, I mean the edge that are not closed up by vertices. So in particular, there's no morphism from Ci to Cj if I is not j. Let's look at the picture on the right. So suppose I want to map C2 to C3 this way, just by this injection of the branches, then this doesn't work because the whole tree on the left is not mapped to a subtree with its outer edge. Because this part is not a subtree without its outer edge. Because if we pick this point, we should include yeah, if we pick this point, we should wait a minute. Yeah, so this part is not a subtree of it. But if we do it for the closed version, it does work because now we are not picking this as a subtree. This is not a subtree, but we are mapping to this full thing with the black edge and the end vertex. So this is the subtree that we are sending this subtree to, and its outer edge now corresponds to this outer edge. So to sum up, I was saying that morphisms in this category is very subtle. And in particular, if we map this open tree Ci to Cj, there's none of them if I is not j. But if they are closed from Ci bar to Cj bar, then any injection will induce a map from Ci bar to Cj bar. And if we want to map Ci to Ci bar, that's okay. But from Ci bar to Ci, that is not okay. It's not a map of trees. Okay, so by saying this, I want to make a comparison of unital operads with some sort of dendrital sets. So the theory of dendrital sets is supposed to be an extension of the theory of simplicial sets and colored operad, like this. And there is a nerve from colored operad to dendrital set. And in particular, if we take an operad and the nerve of it, we can recover the operad by evaluating it at this eta, this root, we will get C0. Evaluating at these CNs, we will get the M space of the operad. And here is a comparison diagram. For an operad, we can do nerve to a dendrital set, and we can forget from dendrital sets to sigma sequences because all the open trees Ci, they form a category isomorphic to sigma. And we can also forget to lambda sequences because all the Ci bars, they form a subcategory isomorphic to lambda. So we have maps between trees when there's an injection. And these two forgetful, there is a natural transformation here. That's because now in the category of trees, sigma, as I defined, is not a subcategory of lambda, but there is a functor from each open tree that maps each open tree to its closure. So it induces for every dendrital set a map from x of t bar to x of t, and this is the natural transformation I was mentioning. And a dendrital set is called closed if this natural transformation is always an isomorphism. So if this map is always a bijection. So now we can compare this to what we said about operads. If an operad is unital, then this is the same thing as dendrital sets nerve of C is closed, or this natural transformation is an isomorphism. But on the left, it is unital if and only if we can extend the forgetful maps to lambda sequences. So this is a detour of comparison of notions. Okay, so now let me move on to the second monoidal structure, the Kelly product. There's some definition here I'm going to make. If we have a contravariant lambda functor, then we can have an associated functor from the category over the unit to itself. Here. So this associated functor will do the following thing. If I have an object under the unit, I can define out of it a covariant functor from lambda to v by mapping n to x tensor itself n times, and the unit tells me how this injection, how to map x n minus 1 to x of n, because I can just map unit to x. Now I have a covariant functor x star and I have a contravariant functor c. I can do a covariant construction which I call a tensor product of functors here. So basically you do Cm tensor x tends to the n, and then you do some base point identification. This is the associated functor of C, and if C is an operad, then this is the associated monad of an operad. And if we have a look at the example of configuration space on n of k points, then this associated functor, what is it? Well, it is going to be configuration space on M, and for each point you picked, you also picked a label in X. And furthermore, if your label is the base point, you can forget it. So that's what the base point identification is doing. Right, now we can upgrade this to contravariant lambda functors over the unit I0. So on the deconvolution, the unit is I0. This is the category under unit. If we have such a lambda sequence under the unit E, we can also do the E star construction to get, just formally, we get a covariant functor from lambda to lambda sequence. And now we can also do this tensor product over the category lambda, and we will also get a lambda sequence under the unit. And we call this the Kelly product. So explicitly, the n space of this construction will be the following thing. You take the k space of C, ck, and then you tensor en1 up to enk such that n1 plus ... to nk equals to m. And then you symmetrify this answer. And then you want to do some gluing. If one of the ni is 0, then this should be glued to a previous skeleton. So without this gluing, if we don't have this gluing, this is the composition product of symmetric sequences. But if we want to do it with lambda, we have to do this gluing, and we will see that this map, if we do composition product versus if we do Kelly product in lambda sequence, this map is now not an isomorphism compared to the case of deconvolution. This is different. And the unit for this monoidal structure is I1. So it's represented by 1. In particular, more specifically, the spaces of I1 at 0 and 1, it is the unit, and at n greater or equal to 2, it is the initial object. And I didn't write it, but I was saying that if we do I1 dot E, this is isomorphic to E. And if we do E dot I1, this is isomorphic to E again. Okay, and this composition product, Kelly product, is strong symmetric monoidal in the first variable, meaning that if we do deconvolution tensor with D prime, and we do circle dot E, this is isomorphic to D circle dot E box D prime circle dot E. And this tells us in particular that I0 dot anything is isomorphic to I0. Oh, okay. And in the proof, we use that the tensor product commutes with colimits in V. And this is mentioned here because we need to use this proposition to prove that the dot product is associative. So if we do not have that tensor product commutes with colimits in V, we do not have that the dot product is associative. Okay, So here is a remark. If we look at the represented functor by k and call that ik, then this is a subcategory that behaves like the integers, like the ring of integers, because now IM deconvolutional box with IN is I of m plus n, and IM circle dot IN is I of mn. Okay, so using this proposition, we can prove that circle dot is associative, and moreover, this lambda sequence under the unit with the circle dot with the I1, this forms a monoidal category. And now, this is the theorem I have claimed. If we restrict to this unital subcategory of this unitary subcategory, so we do not only have a map from I to C0, but we ask that C0 is just I. This is a subcategory that inherits this monoidal structure, and the monoids in this category are just unital operads. So how do we get the structure maps? Well, here is a formula I copied from above that tells me what precisely are the spaces of this C circle dot E, and now I replace E by C. And saying that C is a monoid, that means I have a map from C dot C to C, and in particular C dot C of M to Cn. So extracted from this map, I can get CK tensor Cn1 tensor to Cnk to Cn, which is just C of n1 plus ... to nk. So the structure map of the operad is part of the structure map of the monoid, and the remaining work is just to check that other things match up. So now we have a monoidal category, and we can discuss what are modules in this category over the monoid. Left modules over it have close relation to C algebra. So we can embed the category VI into this category of contravariant unitary lambda sequence by sending X to X tensor I0. So basically at 0, this is X, and at greater than 0, this is the empty space. And this map is a strong symmetry monoidal map. And if we do the monad Cx or the associative functor Cx and do I0, this is isomorphic to the C dot with I0x. And it will embed C algebra into left C modules in the category of lambda sequences. Okay, what about right modules? So we can see that the deconvolution extends to the category of right modules. How do we get this? Well, if we have two right C module D and E, now from our proposition above, we have an isomorphism of D box with E dot with C to D dot C box with E dot C. And now using the structure of D and E as C module, we get a map from this to D box E. So D box E is again a C right C module. And by examining work of Fries in his book, we can see that the lambda sequence are precisely the right I1 module in the category of symmetric sequence. So this tells us that the deconvolution in symmetric sequence lives to some tensor product in symmetric monoidal product in lambda sequence. And this is the same thing as the deconvolution in lambda sequence. So this is an interpretation of the isomorphism we've seen earlier. And also, Fries also examined what's right module in symmetric sequence over the commutative operad. And he proved that right modules over the commutative operad are precisely those that extend to contravariant functor on the category of finite sets. And it's the same in lambda sequence. So right modules over commutative operad are also those that extend to the category of finite sets. Okay. Maybe I'm short on time, so I'm going to skip this detour, which is a comparison to using the deconvolution to interpret the symmetric monoidal envelope. So I'm going to skip this part. Here is an example. If we have a symmetric monoidal category enriched in V called W, satisfying that the map from unit to any object is I the unit in V. Oh, it's still scrolling. If we have this scenario, then we can do a construction to enrich W in the lambda sequence in V. So we can construct a different category HW whose objects are the same as W. And now the morphisms, we look at all morphisms from the tensors of A to B together, and this will form a lambda sequence. And the composition here is just what you would do for endomorphism operand. So you have A to B and you have B to C, and then you can compose them. So this way, naturally you have that automorphism in this category is a monoid in lambda sequence, and maps from A to B in this category is a right module over this monoid, and maps from C to A is a left module over this monoid. Okay, and if we have a monoid and a right module and a left module, we can do bar construction. So we can have a simplicial object whose Qth level is the dot product of these functors. It is a simplicial object in contravariant lambda sequence. And it is related to the monadic bar construction in the following way, that if we take the contravariant lambda sequence X to be I0 of X that we defined before, and we do the monadic bar construction where the monad and the functor, the monad C and functor M are the associative functors of the C and M, then this I0 of this monadic bar construction is the monoidal bar construction with X being the I0 of X. Okay, so let me quickly say something about application to factorization homology. So if we fix the dimension n, we can define a topological category of framed smooth n-dimensional manifold whose objects are many n-dimensional manifolds with a framing of its tangent bundle, and whose morphisms are embeddings of smooth manifolds and a homotopy in the framing space. Then we can do this H construction to this category, and we will get an operad or monoid in this lambda sequence, which is called a little framed n-disk operad. And if we map into a framed manifold, we can get a module over this operad. And now I'm going to skip through this Pontryagin-Thom map. Okay, so what I want to say is that from here we get associative functors dm, drn, and if we have an algebra over it, then we can define a bar construction dm, drn, and x, and this we will call it the factorization homology on n with coefficients in x. And the Pontryagin-Thom map could be upgraded to a map of lambda sequences. And using it, we can get a scanning map. So since I'm short on time, I'm not going to say the details of that. And the upshot is that in the end, we get a map from the factorization homology defined using the bar construction to this mapping space. And this map is going to be a weak equivalence when A is group-like, and it is going to be a weak group completion if the manifold has a copy of R as a product. So if M is isomorphic to N cross R. And this theorem is called the non-abelian Poincare duality theorem, and it's proved by a lot of authors, including Salvatore, Miller, and a lot of others. Okay, so I'm going to end here and thank you for your attention.